Today we will discuss how to extend blast furnace campaign life under high intensity operation where productivity exceed 2.4 ton per meter cube per day. Our mission is to ensure long-term furnace health without intermediate repairs. So this is a real challenge and it meeting with the numerous companies objective or challenges. So we can say the key area of focus include health lining, protection, advanced cooling strategy and innovative refractory solution. Now to understand the context, Visco operates six blast furnaces ranging from 22 to 38 as it's shown in the earlier slide. Historically, in 1960 saw hearth failure due to suboptimal design, but with technical upgradation, BF5 achieved 15.6 years of continuous service producing 30.5 uh, 35.5 million tons of hot metal. And let's uncover what made this achievement possible. And from them, we also try to learn what are the key technologies for long campaign life. So, as we can see that BF number 5 incorporated several breakthrough technologies and and uh, in those technologies the significant key technologies were like these, like microporous carbon block secured the hearth a fully enclosed stave cooling system with precise water flow maintained thermal balance and high resistance Si3N4 bound silica carbide brick reinforce the stack lining. The use of TiO₂ bearing material added thermal and chemical resilience backed by high quality construction standard. Now coming to the cooling system optimization, as we all know, this is one of the strong enabler to extend the campaign of any blast furnaces, and cooling system along with the refractory goes always together. So cooling water plays a very important role in the cooling system optimization. In early days, cooling water volume remains under 4800 meter cube per hour, limiting productivity. After stave damages in 1998, volume was increased to 5570 meter cube per hour and peaked at 5800 meter cube per hour. These optimized cooling enhance the slag crust formation and keep the stave temperature below 200 degree centigrade, protecting the internal structure and enabling stable operation. So these were the key. And for any furnaces where we find that such type of discrepancy, our focus should be strengthening is at least in terms of volume of water, which should be optimum, and by this we can extend the life of the blast furnace. Now coming to the uh, innovative stave-reborn methods. In these, for damaged staves, Visco developed a stave-reborn technique. What is this? This is about the cutting the faulty pipes, uh, linking it to a flexible stainless steel pipe, sealing the gaps with high conductivity castables, and rerouting water to bypass the failure. So, this retrofitting sort of management helps in strengthening the bottleneck in the cooling system. This ensures continuous cooling flow and extended stave service life while maintaining shell hotspot. Now coming to the important process optimization activity in which peripheral gas control was achieved by refining to a geometry, that is the lengthen from 590 mm to 640 to 660 mm and diameter reduced from 140 to 130 mm, stabilizing blast velocity, and these keep the wave of the blast away from the wall. So additionally, this is not only the thing by reducing the dia, the things were achieved. Apart from this, burden optimization, burden distribution matrix also guided in such a way that gas paths become optimal, especially in view of the gases hitting the wall. So we can see that matrix 1 focused on flow control while matrix 2 achieved better gas efficiency, both supporting the hearth hearth protection. So we can say that uh, this taken a overall care of the hearth. Now, hearth maintenance with the TiO₂ additive is also one of the very strong and major activity taken to take care of this campaign. When hearth temperature exceeds 600 to 700, TiO₂ bearing lump ore containing around 2.5% of the batch was added. This ensured titanium level between zero point 0.1 to 0.15 in the hot metal, forming a durable TiO₂ rich layer. These acted as a barrier against alkali and iron infiltration, shielding the lining and extending furnace life. So, coming to the slide where 15.6 year campaign life of BF5 and this result of the 15.6 year campaign without intermediate repairs producing over 35 million ton of hot metal. This success stem from an integrated approach what we have discussed just in the previous slides. This combining cooling effect like stave maintenance, refracting innovation, and what peripheral drive about this is all about the process control. So these all blend, these all activity metrics help in the success story of extending campaign life of blast furnace. So BF5 remains as a benchmark for operational longevity and productivity. So now coming to the learning from BF5 were applied to other furnaces also, like BF number 1 adopted simplified cooling system with significant water saving, while BF7 introduced super microporous block and copper staves. These upgrade position BF number 7 to aim for over 20 years of operational life, showcasing the scalability of this strategy. So operating at high intensity require optimized burden composition, and we also have a high PCI rate, that is around 160, and oxygen enrichment around 4.5% used. As we have discussed all these things in a very beginning of the slide, and the coke and ore were strategically charged to balance the gas flow, allowing a record productivity of 3.1 ton per meter cube per day without compromising furnace safety. So in conclusion, we can say that by incorporating all these challenging aspects, the figure that we are talking about is achieved safely. In conclusion, we can say that long campaign life under intensified condition that we are talking about requires seamless integration of design, cooling, refractory control, and process optimization.